Hello, in this video we're going to continue our talk about limits, and then we're going to talk about continuity. So if you recall, last time we defined limit of a function at a limit point using epsilon delta. So here is one definition. Given a function f from d to rm, where d is a subset of rn, we write down f as f1, f2 all the way to fm, and each of those fi's are called a coordinate function of f. So if you have a function f of xy equals sine of x plus cosine of y, comma sine of xy, comma y squared x, then these three, and this is a function from R2 to R3. These three functions are called coordinate functions of this function. Coordinate functions are basically portions of the original function that go to R. Okay, so here is the first theorem. This theorem allows us to find the limit of a function knowing the limits of those coordinate functions. So let D be a subset of Rn and A be a limit point of D, B be a point in Rm. Assume f equals f1 through fm is a function. If limit of f of x is b, then limit of fi of x is bi, and vice versa. So in other words, if you want to find the limit of f, find the limit of the coordinates, and if you know the limit of f, you can find the limit of those coordinates. Okay, so let's prove this one. This is a by condition. Also, we'll have to do two things. Assume that f of x approaches b, then we will have to prove that fi of x also approaches bi. So assume limit of f of x equals b as x approaches a. And by definition, this is b1 all the way to bn or bm. Okay, so let's write down what this means. So this means for every epsilon positive, there is a positive delta that whenever the distance between x and a is less than delta and more than 0, and x is in the domain, then the distance between f of x and b is less than epsilon. Okay, so we would like to show that in fact f of x and b, we know that f of x and b are close to each other. What we're trying to show is that f1 of x and b1, f2 of x and b2, and so on, those are also close to each other. So I'm going to do my scratch work here in a different color, and then we'll get to the proof. Now, and this is an example for epsilon delta. If you want more examples, this would be one more example. And I have more examples in the notes as well. So this is what we want to prove. The objective is to prove that for every epsilon positive, there is some delta positive that whenever x minus a is less than delta, more than 0, and x is in the domain, then the distance between fi of x and bi is less than epsilon. So from the fact that f of x minus b is small, we want to show that fi of x minus bi is also small. So let's write down what it means for f of x minus b to be small. So what is this? This is the norm of f1 of x all the way to fm of x minus b1 through bm. And this is equal to, if you look at the definition of norm, the Euclidean norm, that's equal to f1 of x minus b1 squared all the way to fm of x minus bm squared. We know this is a small, so we also know that fi minus bi, fi of x minus bi, is going to be less than or equal to this quantity. So if this is less than epsilon, this would also be less than epsilon. So in other words, the same delta would work. Now, so let's write it down. So assume x minus a is less than delta, more than 0, and x is in D. So by what we have above, which I'm going to call star, so by this star, let me move this to this next row. What I get is that the distance between f of x and b is less than epsilon. So the distance between f of x and b is less than epsilon. So what does that mean? It means the square root of f1 of x minus b1. So f of x is f1 of x all the way to fm of x, and b is b1 through bm, all the way to squared plus fm of x minus bm squared is in fact less than epsilon. Now, because all of these terms are positive, every one of these terms is greater than or equal to 0, I can drop them and get something smaller. So this means fi of x minus b is also less than epsilon. And therefore, by definition, limit of, and this is bi in fact, limit of fi of x is in fact bi as x approaches a. And this is true for every I. So we proved one direction. From the fact that f of x is close to b, we proved that in fact each of the coordinates of f must be close to each of the coordinates of b. Now the converse of this one. So assume that limit of fi of x as x approaches a is in fact bi for all I, for I equals 1, 2, all the way to m. We would like to show, again I'm going to use this different color for the scratch work. The objective is this. The objective is to show for every epsilon positive, there is a delta positive that whenever the distance between x and a is less than delta, the distance between f of x and b is less than epsilon. So how do we show that? Well, again, let's see what that means. This means square root of f1 of x minus b1 squared all the way to fm of x minus bm squared is less than epsilon. Now, we know we can make every single one of these is less than, is very small. So if I make this one very small, if I make this one less than epsilon, less than epsilon, less than epsilon, and then I have a square here, and then I can take this square root. Then I would, these would add up to, if I make each one of them less than epsilon, then I would get epsilon squared, then I would get square root of m epsilon squared. But of course this is not less than epsilon. So I have to make some adjustments. If I replace epsilon here by epsilon over m, over like root m, then I would be able to get to epsilon. Okay, so what do we need to do now? We need to use the fact that fi of x approaches bi, and for each one of them, use epsilon over root m. So that's what we're going to do. So let epsilon be positive. So, okay, so let epsilon be positive, and then for that, what we're going to do is we're going to use epsilon over root m for the definition of limit for fi. By definition of limit of this limit of fi of x equals bi, x approaches a. There is some delta I such positive such that for every x, if x minus a is less than delta I and more than 0, then the distance between fi of x and bi is less than epsilon over root m. So this is true for every epsilon. I can just use epsilon over root m because epsilon over root m is also positive. Now, I will have to introduce my delta. I would need all of these inequalities to hold. So I would need my delta to be smaller than all of these. So now let delta be the minimum of all of these deltas, delta 1 all the way to delta m. Since each one of them is positive, since delta a is positive, delta would also be positive. Now if x, and of course x is in D, x is in the domain. If x minus a is less than delta greater than 0 and x is in D, then x minus a would be less than delta I and more than 0 for I equals 1 through m. So that means the absolute value of f of x, fi of x minus bi is in fact less than epsilon over root m. And this is again true for all I equals 1 through m. Now let's take the distance between f of x and b. This is equal to the norm of f1 of x all the way to fm of x minus b1 through bm, which is equal to square root of f1 of x minus b1 squared all the way to fm of x minus bm squared. Now each one of these is less than epsilon over root m, so this would be root epsilon over root m squared, and then you'll have to add this to itself m times. So this is m times. And this becomes the square root of m epsilon over root m squared, which is epsilon. So what does that mean? That means the norm of f of x minus b is in fact less than epsilon, which means by definition limit of f of x as x approaches a is in fact b, which is what we were trying to prove. So bottom line of this theorem is, in order to find the limit of a function, you need to find the limit of all of its coordinate functions. Okay, so the next theorem. So the next theorem is the Squeeze Theorem. This is kind of a familiar theorem. Let D be a set, so suppose D is a subset of Rn and A is a limit point of D. We need all of those because we want to define limit. F, G, and H are functions from D to R, and G of x is a function that lies between f of x and h of x. We know both f and h approach the same number. Then g of x also approaches L. Okay, so how do we prove this one? So again, what we are trying to do is we are trying to show that the distance between g of x and L is small. So let's look at x in D minus A. So what we know is this. We know that f of x minus L is less than or equal to g of x minus L and less than or equal to h of x minus L. So we know that. Now we would like to show this is small, knowing that both of these two can be made small. So I would have to relate the absolute values. So what's the relation between the absolute values? Absolute value of g of x minus L is less than or equal to the maximum of those two. Maximum of absolute value of f of x minus L and h of x minus L. So this is not very difficult to see. And the reason is this. I'm going to use actually parentheses here. That's what I usually do when I do maximum minimum. So if you have a less than or equal to b less than or equal to c, you have to take up a few cases. Absolute value of b is always less than or equal to the maximum of absolute value of a, and absolute value of c. If you take a few cases of which ones are positive and negative, you will see exactly this inequality. Not very difficult to see. Okay, you cannot take absolute value of inequalities unless all sides are positive. If they are all negative, you have to flip the direction. If one of them is positive, one of them is negative, then it's not clear what happens. But this inequality always holds. Now I know this one is a small, and I know this one is a small. So now we can show that this one is small. So how do we do that? So let epsilon be positive. By definition, we know that there is some delta 1 and delta 2 positive, such that if norm of x minus a is less than delta 1 and x is in D, then the distance between f of x and L is less than epsilon. But since I know that that's basically going to be enough, because I want to make sure this is less than epsilon and this is also less than epsilon. So that's good enough for now. Now we'll have to do the same thing. So x minus a, norm of that is less than delta 2 and x is in D. That implies the distance between h of x and L is less than epsilon. Now we are going to take something that satisfies both of these. So let delta be the minimum of these two, minimum of delta 1 and delta 2. Since both delta 1 and delta 2 are positive, delta would also be positive. Now if x minus a were less than delta more than 0 and x were in D, then the distance between g of x and L, which we know is less than or equal to the maximum of f of x minus L and h of x minus L, and these x's are in Rn, so I have to put arrows on top. This would be less than epsilon because both of these quantities are less than epsilon. We know that it satisfies both this inequality, x satisfies both this inequality and that inequality, which means absolute value of f of x minus L and absolute value of h of x minus L are both less than epsilon. Okay, so this means absolute value of g of x minus L is less than epsilon. Therefore, the limit of g of x is in fact L as x approaches a. And that completes the proof of the squeeze theorem. Okay, now that we are done with the idea of limits and some important theorems, we will look at continuity. So you have seen idea of continuity in single variable calculus, and the continuity is defined as the limit at the point must be the same as the value of the function at that point, and the definition is going to be the exact same definition. So what is the definition? Limit of f of x as x approaches a equals f of a. That's when we say f is continuous at a point a. And we say f is continuous at on a domain if it is continuous at every point on the domain. So let's look at some examples, and these are very important examples. Prove the following functions are continuous. Pi I that takes x1 through xn and it gives you xi. This is called projection onto the ith coordinate. So that's called projection onto the ith coordinate. This is obviously the product, and this one is the sum. That's why I call them P and S. So we are going to show that these three functions are in fact continuous. So how do we show they are continuous? We will just use the definition again. So let epsilon be positive. Objective is I want to show if x1 through xn are close to a point, and also let's start from a equals a1 through an inside Rn. I want to show if x is close to a, then xi is close to ai. So we could just take delta and epsilon to be the same. Let me explain that. We want to go from distance between x minus a being less than delta to distance between xi and ai being less than delta, being less than epsilon. But this guy is just the square root of sum of xj minus aj squared, which is greater than or equal to absolute value of xi minus ai. So we can make this one less than epsilon by making this one less than epsilon. So here's what we're going to do. If absolute value of x minus a, or norm of that, is less than epsilon more than 0, then square root of x1 minus a1 squared all the way to xn minus an squared is going to be less than epsilon, which means xi minus ai in absolute value is less than epsilon, which means pi I of x1 through xn minus pi I of a1 through an is less than epsilon in absolute value. So by definition of limit, pi I of x1 through xn approaches pi I of a1 through an. So let me write it down this way. So limit of that, and let me change that to, as x approaches a, of pi I of x is going to be pi I of a. And therefore, pi I is in fact continuous at a. So it's continuous at every point, therefore it's continuous on the domain. Thus, pi I is continuous on its domain Rn. So that's the first one. Next, we want to show that product is also a continuous function. So the objective is to show, again, scratch work would be, we want to show if x comma y minus a comma b is less than delta, then xy minus ab would be less than epsilon. So that's our objective. So how do we show that? Well, we are trying to show that if x is close to a and y is close to b, then xy minus ab is also small. So let's rewrite what that means. So if you write this down as x minus a times y plus, this one would be small. And I know that y cannot go to infinity. Y has to stay around b. So if I add and subtract a y here, I would get this, which is absolute value of x minus a times y plus a times y minus b. Now both of these are small, so I can rewrite that as by triangular inequality as x minus a times y plus a times y minus b. Make sure this is less than, this is a small, less than epsilon. This also small, and this one doesn't go to infinity, doesn't blow up. So we have to first make sure this doesn't go to infinity. So what do we do for that? We'll just make sure that delta is less than 1. And if that's the case, then we would get y square root of, let me write it down, x minus a squared plus y minus b squared, which is less than delta, is going to be less than or equal to 1, which means absolute value of y minus b is less than 1. And that tells us that absolute value of y, which is absolute value of y minus b plus b, is going to be less than or equal to 1 y minus b by triangular inequality plus absolute value of b, which is less than 1 plus absolute value of b. So I will get this is less than 1 plus absolute value of b. Now this quantity that I have here, the first portion, absolute value of x minus a, is less than delta. The second portion, absolute value of y, so this is less than delta. I can replace it with delta. This portion is less than 1 plus b, plus this one is absolute value of b, and this one is less than delta. So absolute value of a times delta. So this we want to be less than epsilon. So we'll just take that, rewrite it as epsilon over 1 plus absolute value of a plus absolute value of b. I have this, and I also have delta less than or equal to 1. And then from here, we get the delta to be minimum of those two. So let's get started writing down the solution now. So let epsilon be positive. And let's start from a point on the domain. So and AB is in R2. So it's a point in the domain, and we want to show that f is in fact, or the function p is in fact continuous at that point. Set delta to be the minimum of 1 and epsilon over 1 plus absolute value of a plus absolute value of b. Now, we know that delta is less than or equal to 1 and delta is less than or equal to epsilon over 1 plus absolute value of a plus absolute value of b. So we know that. So we're going to start with writing down the assumption. So suppose distance between xy and AB is less than delta. So that implies square root of x minus a squared plus y minus b squared is less than delta, which means absolute value of x minus a is less than delta because this quantity is greater than or equal to 0, and also absolute value of y minus b is less than delta because this quantity is greater than or equal to 0. Now let's look at the second one. The second one tells you y minus b, because delta is less than or equal to 1, y minus b would be less than 1, which means absolute value of y is less than or equal to absolute value of y minus b plus absolute value of b, which is less than 1 plus absolute value of b. Now we are going to look at p of x comma y minus p of a comma b and show that this is a small. So how do we do that? We write it down as xy minus ab, which is equal to x minus a times y plus a times y minus b, which is less than or equal to absolute value of x minus a, absolute value of y, plus absolute value of a, absolute value of y minus b. Now we are going to replace this one by delta. We are going to replace this one also by delta, and this one by 1 plus absolute value of b. And this ends up being delta times 1 plus absolute value of a plus absolute value of b, which is less than or equal to epsilon. So that tells us p of x comma y minus p of a comma b is going to be less than epsilon. And therefore, limit of p of x comma y is in fact p of a comma b as xy approaches ab. So what does that mean? It means p is in fact continuous at a comma b. Now since a comma b is arbitrary, p is continuous on the entire domain on R2. And that completes the proof of part B. Now let's look at part C. We are trying to prove that the addition is also a continuous function. So let's see what we're trying to do. The objective is to show that if the distance between xy and AB is less than delta, then the distance between x plus y, and of course positive, minus a plus b is less than epsilon. So this is what we're trying to do. From here, we can get square root of x minus a squared plus y minus b squared less than delta, which we get absolute value of x minus a is less than delta and absolute value of y minus b is less than delta. The idea is the same thing. This is greater than or equal to 0, and also this is greater than or equal to 0. And then if we add them up, we get absolute value of x plus y minus a minus b by triangular inequality is less than 2 delta. We need to make sure this is less than or equal to epsilon, so we just take delta to be epsilon over 2. Okay, so let's start with that. Let epsilon be positive. Set delta to be epsilon over 2. Assume AB is inside R2. If the distance between xy and AB is less than delta, then square root of x minus a squared plus y minus b squared is less than delta, which means absolute value of x minus a is less than delta and absolute value of y minus b is also less than delta. Now let's look at the difference between s of x comma y and s of a comma b. This is absolute value of x plus y minus a plus b. By triangular inequality, this is less than or equal to, I'm using triangular inequality here, absolute value of x minus a plus absolute value of y minus b. Both of which are less than delta, so we get 2 delta, which is exactly epsilon. So that means limit of s of x comma y is in fact s of a comma b as xy approaches ab. And what does that mean? It means s is continuous at AB. So now AB is arbitrary. So since AB in R2 is arbitrary, S is continuous on its domain, on the entire R2. So these 3 examples are actually important. I will do more examples like this in the next video. But finally, the last theorem in this video, and then we'll continue with this one next time. Let D be a subset of Rn and A be a limit point of D. The function f from D to Rm is continuous if and only if each coordinate function is continuous. So what's the reason for that? The reason is basically the limit of coordinates is coordinate of limits. So there is an if and only if here. So let's assume, okay, before I do the 2 directions, let me just assume that f is f1 through fm. So it's a coordinates of this are called f1 through fm. So let's go this way. So since we know that f is continuous at a, limit of f of x as x approaches a is equal to f of a. So we know that since it is continuous at a. Now let f of a be, well, we know what that is. We know f of a is f1 of a all the way to fm of a. So we know that. Now, we know that if you look at the left hand side, f of x as x approaches a, this is equal to, this was a theorem we proved earlier, this is equal to limit of f of f1 of x as x approaches a all the way to limit of fm of x as x approaches a. So what does that mean? That means limit of fi of x, each of these components would be the same as each of those components, would be the same as fi of a as x approaches a. And what does that mean? It means fi is in fact continuous at a. Now the backwards direction would be quite similar. Let's assume that we have these. So it's basically the same thing. So assume fi is continuous at a for I equals 1 through m. When you take the limit of f of x as x approaches a, by a theorem we know this is going to be equal to the limit component of limits. So it would be limit of components. So you will have to take limit of f1 all the way to limit of fm. So we know that by the theorem that we proved. At the same time, we know that each one of these is continuous. So the first one is f1 of a, and the last one is fm of a. And what is f1 of a through fm of a? That's just f of a. So we ended up getting limit of f of x is f of a. And what does that mean? It means f is continuous. So therefore, f is continuous at a. And this completes the proof of this theorem. So in the next video, we're going to go over some examples of continuous functions and some other important theorems. I will see you in the next video.